Most MCP tutorials stop at Hello World, but the real problem starts when your server needs auth, permissions, and tools you can expose safely. This is the setup you'll be able to run after this, which authenticates a user with scoped access and safely invokes a tool on a resource. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Servers that call tools face three problems at once. First, you must know who is calling. Second, you must check what they are allowed to do. Third, you must make sure tools only touch safe files. If any of those fail, a harmless demo becomes a security incident. Success means a short, auditable flow, where a client proves identity, the server checks scopes, a sandbox limits file paths, and a budget prevents runaway costs. At a high level, the idea is simple. Sign a token with a secret so the server can trust it. Map users to scopes and to a path prefix so tools only operate in permitted places. Add a small credit counter so expensive actions stop when the budget is gone. Together, these three guards make a minimal, practical, secure tool server. We will build a tiny example that ties those guards together. You will see token signing, scope checks, a path sandbox, a credit debit, and a guarded read tool that returns file bytes only when all checks pass. None of the pieces are exotic. Each one is clear, and you can replace the toy storage or budget with real services later. Now we'll show token signing and verification. This snippet verifies a signed token using hmac to establish a simple authentication gate. It imports hmac and hashlib, then defines a shared secret used to sign messages. The function sign returns a hexadecimal hmac for a given message, which is used to bind the token to the username. The function verify splits the token into the user and signature, then uses compare digest to safely check that the signature matches the expected value. A token for Alice is created and immediately verified. The printed result shows whether the token passed verification and which user was recovered, proving the gate works. Next, we layer scopes onto the auth result. This example turns authentication into authorization by mapping users to scopes and checking a required permission. It keeps the same hmac-based verify and uses roles to capture each user's allowed scopes. The variable need represents the scope set a tool requires. Here, it's right. After verifying the token for Alice, the code looks up her scopes and tests whether need is a subset of what she has. The Boolean OK reports if the tool can run, and the printed scope count shows her breadth of permissions. The print confirms the authorization decision, which matters because tools should only run when required scopes are present. Now we add a resource sandbox, so access is limited by path. This code constrains which resources a user can see by enforcing a path-prefix sandbox. The list files represents items the server could expose, mixing allowed and disallowed directories. The dictionary base assigns each user a permitted root. Alice is limited to docs/. The function visible filters files by checking that each file starts with the user's base path, then sorts the result so selection is stable and predictable. The variable v holds the filtered list for Alice. The print shows how many files are visible and the first allowed file, confirming that the sandbox correctly hides logs and secrets while exposing only docs. Next, we add a small budget to limit costly tools. This snippet adds a simple credit budget so costly tools can be limited per user. The budget dictionary tracks remaining credits, while cost specifies how many credits a tool consumes. The function charge subtracts the tool's cost from the user's budget clamps the result at 0 to avoid negatives, and returns the updated total. The call with write docs demonstrates a single debit against Alice's budget. If you increase the tool's cost, fewer calls will fit into the same budget. If you raise the budget, more calls are allowed before throttling. The printed remaining credits confirm the limiter updated state and will bound future calls. Finally, we wire auth, scopes, sandbox, and budget into a guarded tool call. This snippet ties the guardrails together into a minimal, secure tool dispatch. The roles mapping ensures the user holds the read scope required by the tool. The base dictionary restricts resource paths, so access is limited to docs, forming a sandbox. The budget tracks remaining credits and is decremented with each allowed call, making usage enforceable. The function read file evaluates all 3 checks, short-circuiting to none if any guard fails, then returns file content from FS when successful. The result, res, reflects a permitted read of docs.btxt. The printed status and bulk count confirm a successful, properly authorized, and budgeted tool run. In a real project, you map the tiny in-memory store here to your user database, your persistent budget ledger, and your real file storage. The same checks scale, sign and verify at the edge, check scopes from your identity provider, enforce a path mul or object prefix, and decrement credits in a transaction. Recap: it is a compact pattern that combines token signing, scope checks, and a path sandbox with a budget. Use it when you need to expose tools safely to untrusted callers or to third parties. One caveat is that the shared secret and budget must be stored and rotated correctly. Otherwise, trust and limits break. Next step: measure and tune the budget cost and scope granularity. Increase or decrease the cost per tool to see how many calls fit per user, and consider splitting core scopes into finer scopes for safer delegation. If practical AI engineering and secure tooling help you, subscribe and watch the AI engineering videos.